Previously, I've talked about how using what we know of the distance between the two gaps and the distance of the screen and the wavelength, we can calculate x. We can calculate the spacing between two fringes. This interference pattern, this interference effect, is also useful if you want to calculate the wavelength of light. We can just take this formula, and turn it around and say, right, if I want to find a wavelength, I can do it if I know the distance between the gaps, distance of the screen, and the distance between the fringes. Right? If we know these three numbers, we can then use this same formula to find the wavelength. But if we actually do this, if we actually try and do this, there is one difficulty, and the difficulty is that if you look at the fringes, sure, if I can just put a ruler next to it and measure the distance between, say, this bright fringe and the next bright fringe. But as you can see, each of this bright fringe is quite broad. It's quite broad. So it's not like two sharp lines where I can just easily measure the distance in between. We have two bright spots, right? Two blobs of light. So exactly where from one fringe do I measure, and where in the other fringe do I stop? Right? Where do I measure from and to? So I can roughly say, right, measure roughly from the middle of one fringe to roughly the middle of the other fringe. But if it's roughly, then it's not going to be very accurate. So it would be really good if there is actually some way, we can maybe change this setup so that the fringes become narrower. And indeed, there is such a way. And the way to do it is by adding more gaps. So in this double slit experiment, we have two slits, or slits and gaps, or gaps. So we have two slits. Now we can add another slit, maybe at the same distance away, or we can add even more slits, and doing that will have the effect of making the fringes narrower. So let's look at this in a little bit more detail. Now if I look at this fringe pattern, now let's think about maybe plotting a graph of the intensity along this direction. Okay, so let me call this direction the x direction. So that's my x-axis, and that's where x is 0. Okay, now suppose that I want to plot the brightness or intensity along this axis. So I could try and draw a graph. Try and draw a graph like that. Okay, now you can see from here that I would get fringe pattern that might look like this. So at the center, at x equal to 0, I would have a bright fringe, and then the next bright fringe, and the next bright fringe, and so on. Likewise for this other side. So let me label this a little bit. So this one at the center, this one here, is the center fringe. Maybe that one. Yeah, I'll call that maybe A. So that one is A. So imagine that if I move along here, all right, it goes bright, dark, bright, dark, bright, dark. So I plot the graph of the brightness. So A would have a peak for this one, and the next bright fringe, if I call that B, would be that one. If I call that one C, that would be this one, C. Okay, so in between A and B, for example, is a dark fringe. That would be this part where the intensity comes to 0. So this is like an intensity or a brightness graph against X, against this axis. Okay, so this is what it would look like. And as you can see from the graph, the distance between two bright fringes would be, say, this one. Roughly from the one peak to the other peak. So that's the distance. And it is not very obvious if you use a ruler to measure. Right? It's not very obvious exactly which point to which point you should measure. You know, roughly it is to the peak. Okay, but the peak is quite smooth, so it's not clear exactly where. Now, in order to make this more accurate, it would be nice, as I said, if there's some way to make this peak narrower, so that we know more exactly where say the center of the bright fringes. Now, and the way to do it, as I have suggested, is to add more slits. So I have two slits here. I can add one more slit there, for example. If I add one more slit there, then what happens is that slit would also produce light going to the screen, and at say at this point where I expect a bright fringe, I would in addition to the light, the wave from the original two slits, I now have wave from the third slit. Now the interference condition is the same. For constructive interference between those two slits, the path difference has to be a whole number of a wavelength. Okay, if I have another slit, now I have to use the same, let's see, the same spacing between slits, so that's A, and this distance must be A also, from there to there. I have to use the same distance, and the path difference between of the wave from this slit to the next one must also be the same as this. So if that's one wavelength, this is one wavelength. If that's two wavelengths, this would be two wavelengths. Okay, the reason is as before, we may assume that this screen is quite far away compared to the distance between slits, so that those three rays, I mean, they don't look parallel as I draw it, but because that is actually very far away compared to this spacing, okay, those three rays are actually very nearly parallel. They're very nearly parallel. So it's the same interference condition, right, between the path difference between waves from two adjacent slits has to be a whole number of wavelengths. So that's the difference here. We have an additional wave from the additional slit coming here. But what effect would that have? Well, see, if I had just the two slits at first, we understand that there would be constructive interference here. When the path difference is one wavelength, there would be constructive interference here, because the peak from one slit would meet the peak from the next slit, and they would interfere constructively. But if the third slit, since the third slit is at the same distance away and has the same, and therefore has the same path difference, the peak from the third peak would also arrive here. A peak from the third slit will also arrive here at the same time as peaks from those other two slits. Alright, so we have peaks from all three slits, maybe coming out from the slits at different times. Okay, but they all reach here at the same time, so they will all add constructively. Okay, so we can still understand that there would be constructive interference here and a bright fringe here. But the question is, how can this make the fringe narrower? So let me take a closer look at this graph. Take a closer look at this graph. Now, so we understand what happens at the peaks, maybe at this point, at this point. Alright, so that's the B here. So at this point, which might be here, where all the peaks meet, we have constructive interference. That's why we get a peak. But what happens in between two peaks? Now, in between two peaks, we understand, for example, when we are here at this point, we understand that say the peak from one slit would meet the trough from the other slit, okay, which is why we have cancellation here. But things get more complicated when we have a third. When we have a third slit, we may not actually have exact cancellation in the middle. Okay, so in the middle, it might not be completely dark actually. But what happens is it also makes things more complicated when you're, apart from the middle, things also get more complicated around here and here. When you are around here or here, because there are more waves, they would be more likely to cancel each other, and as a result, the intensity around here would actually come down, right? Because there would probably be more cancellation. So as a result, we would get less intensity around the middle between the two bright fringes. So as a result of that, okay, let me draw another graph for this. If I plot another graph, so that was my A, that's my B. So as a result, these two regions would most likely come down more quickly because there's more cancellation. And this is what I would get between A and B. Okay, I would get less intensity. And if you compare this peak with this peak, or this peak with this peak, you see that this means that the peak has just become narrower. Alright, because there's more cancellation in the dark fringe, around the dark fringe area. So if I sketch this for the other peaks, I will get a similar situation. So the result is that I start getting narrower peaks because there's more cancellation in between peaks. And what happens if I add even more slits? If I add another slit up there, if I add some more slit down there, then if we repeat the same reasoning, we would expect that at the original fringe, at the center of original fringe of each fringe, there will still be constructive interference because the path difference between adjacent slits are the same. Peak from one slit will always meet the peak from the next slit, but in between fringes, the more slits you get, the more cancellations you will have. So in between peaks, the intensity will get, the brightness will get smaller and smaller. And as a result, the peak itself, each peak or each fringe would get narrower and narrower. So if I have lots of fringes, lots of slits here, I can get very, very narrow fringes. Now, how narrow? It depends on how many we have. Remember that this spacing is actually very small compared with this distance. All right, this is an exaggerated diagram. So I can have hundreds or even thousands here. Okay, and the whole stretch of slits will still be quite short compared to this distance. Could still be quite short compared to this distance. So it might look something like, for example, just lines. It might look just lines, narrow lines that we have for the fringes, because there's so much cancellation in between peaks. And once we start getting narrow lines, it becomes a lot easier to measure accurately the distance between the fringes. And that makes it more accurate if we want to use this to calculate the wavelength. If you remember using that formula, lambda over A is approximately x over t. Okay. Now, having understood this effect, this possibility that we can make the fringe a lot narrower just by adding more slits. Now let's continue to think about this a bit more and see if there are other ways to make it even more accurate. We can do things like, for example, reduce A. Right, we can try to make A smaller. For example, if A is smaller, x will be bigger. Okay, because lambda divided by a smaller number will give a bigger answer, so that's why x can be bigger. And if x is bigger, it's also easy to measure more accurately. All right, if you measure a bigger distance, you'll get less percentage error, less percentage error in the measurement. So that's one thing. We can try to make A smaller. We can have more slits to make the spacing narrower. And one more thing, we have an approximation here. That's an approximately equal to sign. If I can somehow make that exactly equal, or change the formula a bit to make it exactly equal, then that would also make the measurement of the wavelength more accurate. So I shall explain how to do this in the next session.